You hear me? Check, check. Good. All right. Good afternoon. Welcome back. At least I'm back. So a couple of things first. Number one is next week still has some little strange things happening, so there's no class on Monday. And then from then on, we're just going on the regular route as basically explained on the syllabus. So no surprises here anymore. My travel is basically done, which is good. So I'm around. A couple of other things. I looked at waiting lists and things like that. That should be all resolved. Basically up the class list and things like that. If you're on the waiting list, you should be enrolled now. There's one student still, and I don't understand 100%, there's still one student who's on the waiting list for 151. There's absolutely no reason why. I think it's because of one discussion session. If you have that problem, the person that has a problem, just put yourself in the other discussion session and you're going to be fine. You will get automatically enrolled. If you're I have approved all the concurrent enrollments. So if you're basically in that boat, you're all set as well. At least the whole paperwork is going through. So that part is out of the way. Let's see what else in terms of practical things. Labs are going their way. Make sure you keep on track of them. Because semester is going to go faster than you think. In about 4 or 5 weeks from now, we're going to start talking project. So that means that you're going to have the tools in your hand, that you know how to play around with all those idiosyncrasies and things like that, all the weird stuff. So keep on track on the labs. Homework number 2 has been posted. So it seems like we're basically running. Any particular questions, concerns, issues at this point in time? Administratively. Everybody's settled? Good. Let's see. The other question I have is any particular questions regarding the material? Everything's cool and easy so far. Yeah. It's not going to stay. Well, yeah. We're going to pick up the pace a bit in the next week or so because obviously there's a lot of things to be done this semester. So the class is videotaped, so it's good. So you want to watch it again for your friends who couldn't make it today. From the time I have the basic tape, it's going to be on YouTube, and we can just post the link on the B-Courses website. All right, so what I'm going to do today is talk a little bit more about Verilog. Combinational logic first, and some of the different styles of description in combinational logic. And then we're going to talk a little bit about sequential logic. You cannot build a computer if you don't have memory. A computer without memory is doesn't do very much, right? So memory is an important element in anything you do. So building elements and how you describe that is going to be very important. And then we're going to go back to combinational logic because a big part of what you learn to do is how to make things good. Make them faster, make them better, lower energy. Typically, that will require manipulation, transformations. Transformations of your logic, transformation of your structure in such a way that, again, you get faster or lower energy and so on and so forth. Okay? So you have to know how to manipulate Boolean expressions. And again, you can say, hey, I don't have to know that because Synopsys knows, which is one way of thinking. But it helps to understand how you can manipulate and what the impact is. So some of the basic rules there are very important. And how you can actually know that what you're doing is correct is even more important. I'm trying to say, I show you one thing and I show you another thing and say, are they the same? Do they do the same thing? And some of them might be described, put this a little bit lower. Some of them basically are obvious. Some of the things are, if I have you a schematic diagram with a whole bunch of things, gates, and here I show you a set of equations. And I say, can you prove to me that the two are the same? That's a hard question. It's not a trivial question. And you can actually prove that some of those things are basically extremely exponentially hard. So these are the type of things we need to think about. But again, what I want to recap from last class is, if you look to Verilog, there's two very different styles of description. One of them says the circuit or a system or a module is nothing else than a connection of modules. It's compositional, it's hierarchical. I have a library of things, of gates and memories and blocks, and I put them together and I make something more complex. We call this, in normal jargon, we call this a net list. A list of nets of components. The behavior really comes from the connectivity and what the individual components do. The other approach is what we call behavioral, where you say my design is basically a function, an input-output function, and I'm going to describe that function as a set of equations. Okay? A set of equations that all hold together. Now here, when it's structural, I can go, since I already have told you the composition, you can go directly to hardware because you have your basic blocks, and I take the basic blocks and I combine them all together, and then I have a tool that basically makes the connections. I can go directly to hardware. If you have something that's behavioral, and mapping this into a particular engine is going to require something like a compiler. Right. Now, we don't call it a compiler when we do hardware, we call it a synthesis tool. Something that synthesizes some lower level from a higher level description. Right? And that's really where Synopsys shines as a company. Again, very simple example, I showed you this before, really shows how you can have both of them together in a design. For instance, I have one element here, which we call a full adder. We'll come back to a full adder later. A full adder, and I describe the full adder just as a set of equations. This is a set of Boolean expressions. And there's one R and one for the sum output and one for the carry out output. Both of them hold at the same time and always hold. It's a set of equations. The order doesn't matter. The other part here is a composition. It says, well, if I want to build a bigger adder, I just take 4 of those that I already have, and if I can write the wires between them, I'm done. Right? Purely compositional. I combine things together to make something more complex. That was easy. And then we start messing things up. I said, well, that set of equation things is kind of bizarre for us occasionally. We're going to make it a little bit more complicated. We're going to add things that are not always valid. It's only valid when something happens. The always statement. It says, you know, this equation here, out is equal in 1 and in 2 and in 3, is only going to be evaluated when in 1, in 2, or in 3 is going to change. Otherwise, we don't evaluate it. That is not holding anymore. So this is kind of a novel computational model. We call it an event-driven model. It's only when you have an event on one of those 3 inputs that we're going to evaluate the output. And I explained to you last class why this is important. Sometimes you have things like case statements where you have multiple options, and you cannot have 3 equations describing the same thing at the same time. So you only evaluate it when you basically have your inputs in and say, okay, I'm going to only pick that one, and then the other ones don't count. But far more important, as you will see, is to describe things which have memory. You have registers, we need something that's event-driven. Come back to that later. That's where the primary use of this is. Remember, every time you have an always block, this is an assignment, but kind of bizarre assignment. You see there's no assign out. We did before, so it's, again, syntax is a little bit messed up, just to make it harder for you. Right? That's the only reason they did that. They could have done assign out, but they didn't. And also we call any variable that's defined in an always block a register. You can see why they were thinking about that. Again, they had confused minds. You can see that this is not a register in this case, but they still call it a register. Okay? Seen that. And again, as a repetition, the always block also helps us in case like case statements. Cases are very useful. A case like I have a bunch of inputs like a select signal, and I want to take, depending upon the select signal, which is 2 bits wide, I want to select in 0, in 1, in 2, or in 3. Nice, beautiful multiplexer type of statement, very easily expressed. 4 different expressions for out. And it cannot all be valid, so it's only when we can know the values of select that I know what to do with the output, which one to pick. I look at the selecting and say, okay, this one is valid, the other ones are not valid. Okay? So that's an example. Now, I could also describe the same thing in a different way. Here's another description of my multiplexer. I have the same thing as, okay, in 0, in 1, in 2, in 3, select. I have 2 bits in my select. So let's assume that if select is 0, 0, then the output should be in 0. Else if select is 1, it's 1, it's 2, it's that, it's 3, it's in 3. Behaviorally, this is completely identical. Again, we have multiple definitions of out. We still use an always statement. Both of our equivalent, so I can use case statements or I can use if then else, but there's some difference between the two. Do you have an idea what the difference could be?
I have a question.
Yes?
So when will this always block be triggered? Like you put everything just inside?
It will be triggered if any one of those signals changes. So from a time, again, this looks at it like a simulator. Again, this is purely simulation vision. So what should I do? What can I do from my simulation perspective? Simulation looks at, oh, this signal, for instance, somewhere else, I get a new value to in 0. So when that's the case, then I have to evaluate this block. And it's going to do. Otherwise, it's not going to look at that block at all. It basically is non-existent. Okay? So if else, else is another way of describing a case statement. Can you imagine, can you kind of figure out what the difference is between the two? Why you would use one versus the other one?
It will create latches. I'm not sure, but this is not all those input, they are not equal to each other.
You're hitting onto something, but you're not completely there yet. Yes?
Is that structure fixed and the other one is like more flexible?
No. I think I can do both. I think I can do a case statement. I can start with the first row, as is if this, else if, else if, else if, else if.
Actually, I think the point is that it will make the circuit become something like a sequential. Like the first signal coming in, it goes to the second block.
You're on top. If I basically would look at this, think about this as how would I build this as hardware? Well, first I have something that checks if select is equal to 0. Check that, and then I do something. Then, if it was not 0, I'm going to do the other one. Then I'm going to do the other one. You see sequential behavior happening here. You force an order in your hardware. So this result will come out faster than this result. And so there's a difference in delay. In the case statement, we all do them simultaneously. It's one shot, and you say, okay, and this one goes, if you think about this as a multiplexer, if I could draw this as a multiplexer, what I have is this here. I have 4 inputs, 2 inputs, 1 output. I look at the inputs, and I route this one, this one, this one, or that one to the output. The delay is all the same. In the other way, it's not that. In the other description, I use if else. I'm going to make a chain. I say, okay. I'm going to say here, let's say in AND structure, this is in 0. If this connection is true, then I'm going to feed it through, and then I basically make a chain of events, either multiplexers or gates or something like that. So you can see that I might have multiple different, that are longer paths, depending on where you come in. So you create sequential behavior. So what I want to point out here is that the way you write your code can have a big impact on the performance. It does the same thing, but by nature you're already building something that is really constrained into it. Okay. One more thing before we basically go to sequential. You see my adder 4 here. It's kind of nice. I use hierarchy, which means that I can build, I only have to describe this full adder one time, and then I can repeat it. But now I'm going to ask you to build a new microprocessor which has 128 bits. That's painful. I have to write this 128 times. That's kind of not something you like to do. And if I know, say, well, I want to do a 1,000,000-bit memory. 1,000,000 bits, basically another cell, another cell, another cell, another cell. Now we should have something that helps us to kind of make, let's say, a adder which has a variable number of bits. So I want to get a 32-bit adder. Well, I'm going to generate it, and I don't have to write it out, but the same software, the same code, I would like to use for 16 bits, 128 bits, and so on and so forth. So Verilog has something for that. It's called the generate concept, a generator. Something that allows you to generate modules of different lengths. Okay. So here's how it stands. So this is a ripple adder generator. By the way, before I go there, anybody has an idea why we call this the ripple adder? The carry ripples through, right? Slow. If you think ripple, think slow. If I want to build the fastest built microprocessor in the world, I'm probably not going to use one of those ripple adders. If I have a 128 bit, the worst case spot goes like this. Goes through all that hardware. So ripple is a way of building an adder, just as a side effect. Okay, so here's an example of how I can now build an adder which is n bits wide. I'm not going to tell you in advance what the width is going to be. So we create the same thing as before, module adder, 2 input vectors A and B, and an output vector R, which is your sum vector. The input vectors, so now we're going to do one thing. We introduce a parameter n. N is equal to 4. N is not a real variable in the hardware. It is something that I'm just going to use to generate. It's not something that basically physically going to translate in anything on your chip or on your FPGA. And then now I can define my A and B as n-bit vectors, and my output as a n+1 bit vector. You add 2 n-bit numbers, the output is always going to be 1 bit wider. So 1 bit wider, and we define some intermediate signal C. So that's one thing, parameter n. When I define that parameter, I can give it a default value. Say if I don't define anything, this is going to create me a 4-bit adder. But I can override it later. Another thing here that's new is this genvar. So we have the parameter. Genvar is a variable that only exists in the specification. Again, it's not something that exists in the final circuit. It's just like a counter or an index. So what I'm saying now, generate and generate, so these are the generate concept. For I equals 0 to n, a+1 begin bit, and then I basically define a number. I define a full adder with a input A, B, Ci, Co, R. And I picked the right bit out of the input vectors or the output vectors. I use I. So I kind of generate a netlist. Right? And you can see this is very powerful. I can do all kinds of things with this. I can generate many big blocks. Makes it a lot easier. Obviously, I'm not completely done. In the end here, I have to connect the first carry input bit to something. Typically, it's 0. And I have to connect, basically tell me that the Cn is ultimately the last carry out is also the last output bit. Is my n+1 bit at my output carry. Right? So, beautiful concept, really helps you to make big things. And then when you want to instantiate it, so I can just call adder 4, and I just call it without anything. Or if I want to basically override the parameter n, I have to say, hey, by the way, I'm going to call I make another adder 64. Here are my input-output vectors, and I'm going to set the parameter n to 64. Again, be careful with the syntax. It's not something which is kind of trivial. You have to have the hash, but the thing and it says dot n parameter n gets a value of 64. And it overrides this, and it's going to generate your. This is something you're going to use quite a bit. Okay? This is very typical. Yes?
That beats part of the syntax for loops?
Sorry?
That beats at the end of the for line. Is that part of the syntax? Beats.
This one here?
No.
The begin.
Yeah.
Yes. You have to have the bit there.
What is
I have no clue what it means. You have to put bit there. Yes?
Oh, sorry, is that just a, like something like just a help message to this
I don't know. To be honest, the syntax requires you that you have that bit statement there. Begin bit. Again, it's not the most aesthetic language, as you can imagine.
Professor,
Yes?
when we're going back, so for n, in the adder, when you're instantiating a model adder, you used like .n, but n wasn't one of the arguments
That's right.
for the adder, so
Mhm.
you can still access it because you defined it as a parameter.
That's right. So it's defined as a parameter here. Obviously, you would get an error if I would have .x64 here or something like that. It's going to check if that's an existing parameter.
So even
But
though
you can see it's not in the port list. This is your port
Yeah.
list. This is in between your adder and your adder name. You basically put that instantiation of your parameter there. Yes?
So that doesn't permanently change n, it only changes n for that instance.
For that instance. Because now, what I could do is I say adder 128, adder 128. I can call adders of different lengths. Now, it's just when you call this, think about this. This is compile time. When you compile this, okay, I'm going to replace n by 64 and execute that generate loop. From that thing, all those variables are gone. They disappear. And in the end, you have an unrolled netlist that basically has all those 128-bit instances all sitting there, or 64. Okay? Good. All right. More on the generate loop, you can do virtually anything. You can create declarations, modules, use define. There's a whole bunch of things I can do with that generate statement. For instance, here's a simple case. It doesn't have to be physical. It doesn't have to be structural. Like in this case, this defines a gray code to binary code converter. Are you familiar with gray codes? Ever heard about it? Gray codes are this nice thing that every number in the sequence is only one bit different than the previous number, or the bit numbers around. It's a great thing to have. Sometimes it is something you might want to use in hardware. So this is, as you can see, this is a behavioral description. There's no module instantiation here. I just send an equation, but I want to use a set of equations. I want to write down n equations. Rather than writing them all down, and for a fixed size here, I say, okay, I'm going to do a 8-bit decoder, so I'm going to define a parameter 8. I define my inputs and output, and I just generate the right equations. Okay? So you can use this for many, many different things. Think about this kind of a code generator. That's the way I look at it. All right. And see the bit here is there again. Something you have to live with. Okay, so last example on the combinational part. Now I'll show you how powerful Verilog really is. Right? Suppose I want to make something which is an ALU. I want to describe it, and I want to make a piece of hardware that does 30-bit ALU. Somewhere, somebody has defined me what my ALU should do. This is my instruction set of my ALU. It has 5 instructions. It can do addition, subtraction, and multiply. And from the addition, I can do both add B, 2 numbers together, or I can increment A. And I can do subtraction, A minus B, or I can subtract B, 1 from B. And these are this is your instruction set. Depending upon the values of F2, F1, and F0, I'm going to select one of those instructions. So my block has two inputs, A and B, right? One output, R. And that's really what we want to do. So you can see, if I look at it from a hardware perspective, I probably can use an adder, a subtractor, a multiplier. And then based on the selection of F, like for instance, if F is equal, you can see that if this bit, F0 is 1, we're going to do the plus or minus 1. If it's 0, we're going to basically add B. So before in front of my adder, I have basically the adder here, take value A as one input. The other input is going to be either B, when F0 is equal to 0, or it's going to be 1 when F0 is equal to 1. Same thing for the subtractor. You have the multiplier, and then I have three results. This one, this one, this one. I'm going to pick which ones I'm going to basically feed to the output based on the values of those two bits here. If it's 0, 0, we do plus. If it's 0, 1, we get minus. If it's 1, 0, we do star. What do we do when it's 1, 1? We haven't told you. You can do anything. It doesn't matter. It's an illegal result or it's a random result because it's not an instruction I have defined. Okay? So this is kind of interesting. What I show here structurally, already I tell you, I already give a lot of information of how I want to see this implemented. With the multiplexers, it also tells me that I'm going to do the plus, minus, and multiply all in parallel. Even if I'm going to pick only one, I'm going to do all three of them. And then pick one's result. This could be good, this parallelism, but it's obviously going to take more power, right? Because I'm going to do this multiply while actually I just need to add. So I'm wasting energy in this particular case. So it's concurrent, but it's maybe not the most efficient way. But that's a choice you can make, and here you can see by that structural diagram, I can define a lot of what I'm going to do. So how does it look in Verilog? Well, it's fairly straightforward. I'm making 2-to-1 muxes, 3-to-1 muxes. I have an adder, I have a subtractor, and I have a multiplier. Multiplier is a little bit tricky, because if I look at my input words, there are 32 bits. Adders, 32-bit, 32-bit, you get 32-bit or 33-bit, depending if you basically chop off the sign bit saturation. The multiplier doesn't work that way. If you do 32-bit by 32-bit, you get 64-bit out. So we're going to do something here. We're actually going to use only 16 bits of the input words and use those as the input to the multiplier and get 32 bits out. So that's already a decision that you make here as well. It's functionally is going to determine the behavior of your ALU. The multiplexer is described using case states. That's a three-input mode. There's something interesting else here. Look at this multiplexer. Is there anything that basically catches your eye in that description? Yes?
Default is X. What is X? I don't know.
Good. Exactly. So it's a three-input multiplexer. And you have two input signals, 0, 0, 1. What's happening when this is 1, 1? I haven't defined. There's a couple things you can do. It says I'm letting the synthesizer define this or whatever, or I can basically say, okay, I'm going to set it all to zeros, or X's means undefined. I say I don't care. It's also effectively an X is called a don't care, which is good because then maybe sometime when I synthesize the hardware, the compiler can decide, it's more efficient to make it a 1 or a 0. I can make it a little bit smaller if I do it that way or the other way. So it's not going to bother me whatever you do. That's what an X is. So you also in the homework, people have asked about the Z. And in one of the homework, you had the Z, the high impedance thing. There's another state. So a binary signal can have 4 different things. You have a binary signal X, let's say. You can have 0, 1, X, or Z. X is, I don't care, as we just said. Z means high impedance. It means it's not going to do anything at the output wire. It's going to basically not impact the output wire it's connected to. Let me give you an example. I have a bus in a computer, and I have here a multiplier, and I have, I don't know, some adder, complete ALU, and this is my bus. So all of those things, like you have memory bus, this goes to the memory. So I have a memory block here. Obviously, this cannot work. If I would connect the multiplier and the adder and the ALU, they all kind of try to drive the bus. And if they don't agree, what happens? If this guy says, no, it should be 1, no, this guy says it should be 0. Something has to give. And your chip is going to fail. What high impedance says, I'm going to put this in high impedance state, which means like I'm not going to try to drive that wire at all. You can consider me as disconnected from the bus. That's the high impedance state. Again, that's something that's going to come back. X's we're going to use as well. If you a clever use of X's sometimes can help you make things a little bit more efficient. Okay? Okay, and here's my whole ALU. I have my modules I just described, and this is the ALU, how I describe it. I have a multiplexer. I give them names. As I said, it's always a good idea to give them names. So I call it my mux here, or subtractor, or multiplier, or adder. I give them their own name because it's going to make it easier when you simulate it to figure out where it is. And as you can see, what we also did here is not do the fixed order. We always name the input you connect it to of the gate. It makes it more crisp. Yes?
Is the fact that 2 of them are named MUX32.2 a typo, or is there significance to that?
MUX32.2 is 2 inputs.
Okay.
MUX32.3 is 3 inputs. Again, that's the naming they used. There's 2 different multiplexers we have. Okay, and we have some intermediate thing. But you can see, in no time, I have described this thing. You have used hierarchy, and I put it all together. Now, as I said, this already said a lot about the implementation. When I start working on a project, I might not even bother yet about the implementation precisely. I said, maybe I could do this behaviorally, right? So I could also describe my whole ALU like this. It's the same thing. I make a case statement and have here basically my F signal, all the particular values of F, and I just write down R is equal A plus B, 1, A minus B, and so on and so forth. Where's that coming from? Anyhow. So here is a perfect example of how you use a case to basically execute instruction sets. Right? This is my instruction set. Depending upon instruction, I basically multiply it out. This doesn't say me anything how many multipliers or adders and what is going to be done. I might be having one unit that I'm going to basically use and reprogram based upon the function I'm going to apply. I have made no decision. This doesn't implement this. They're functionally equivalent. This thing is annoying. They're functionally equivalent, but this has a lot more constraints than this one has. Right? So what you do in design, typically you start, it's good to start with this because you can simulate it and say, okay, this does the right thing. I'm not going to think about hardware yet. I just want to make sure that I have something that has the right function, and then I start replacing it. So I know how to do this. I want to make it fast. I want to make it different. So then you start basically putting structural in there. Okay. Simple rules. In Verilog, we're going to use, so a couple of things that we're typically going to do in the end. Before you go to synthesis, bottom of the hierarchy always has to be somewhere behavior. Or it has to be a predefined element, which is also behavioral. Because if I don't have behavior, I don't know what it is. Right? So I start with behavioral blocks. For the rest, we're going to use primarily structural to define the hardware. If you want to manipulate the hardware, you use structure unless there's certain circumstances that, like, you map to an FPGA, and there's a particular block on that FPGA that you would like to use. Okay? Definitely use instantiation for that. So we're not going to use behavior. Say, hey, use that FPGA block. Or you use ASIC resources that are not supported by synthesis. Right? And then every higher level, we basically try to use basically structure. We try to use continuous assignment as much as possible. Avoid always blocks. Because always blocks can do weird things. Definitely you have many of them. I'll talk a little bit more when you talk about sequential thing. Parallel always blocks evaluate in parallel, and they can do weird things that you don't expect. So the only reason you should use always blocks is for things like case statements or for memory, because they're the only way to describe memory in Verilog. Okay? Use name ports, right? The ones basically, if you call a unit, just don't think you remember the list of the names. Say this name, port A, I'm going to give connect to that net, port B, and connect to that net. You're always going to be safe. Otherwise, you can get weird bugs that's going to take you a long time to figure out. If something doesn't work correctly in your hardware, where's the bug? And if you basically had just flipped two inputs in the call of a module, things could go badly. Help readability and clarity. So for instance, don't use large nested diffs. That's a pain in the neck. Verilog is a big language. There's a lot of bizarre stuff. So we just gave you a first glimpse. Go to Harris and Harris, chapter 4, has a lot of other things. Actually, it's a very good reference. More than enough they need for this course. And then go to the web. There's tons of code, Verilog code on the web. Don't trust it all. Like anything what you get for free, exactly is what you get. Right? There's a lot of horrible code out there. So I would say, be critical. When you load something up, again, it's great if you say, well, I want to do that, and there's somebody as an example for me. That's cool. But look at it very carefully. Yeah. And again, as I already said, the quality of what you're going to get is determined by the quality of your Verilog. It's true for C programs. It's true for any program. You write something, but it's even more important in hardware. I already showed that example of the if then else versus a case. There's a lot of unintended consequences that happen. So I always suggest that before you start writing code, you sit there, I'm going to have this brilliant idea, I'm going to design this module, and you start typing. No. Take a sketch, take a piece of paper and sketch it out first. Just get in your head what you want to do, play around with it, and then enter it, because it's going to save you a lot of time. All right. Any question on that? So let's move to sequential. That's an important part. Anybody who's not familiar with a flip-flop? You all heard about what a flip-flop is. You've heard about the basic memory element, right? Okay, so that's good. That's some time. So what do you need memory? Well, it's quite straightforward. I'm just going to give you an example of why if I don't have memory, there's certain things I cannot do. Suppose I want to do something that counts a sequence of numbers together. So I have a sequence of number x. They come in one after the other one. And I want to add them all together, accumulate it. So what I can do is say, okay, I have an adder, and I take the output of that adder, and I add it out here, and that's my output. Makes perfect sense. Right? I keep on adding, and I take the result, and I put it back. Will this work? Why not?
It should be the same.
Yeah.
There's no guarantee that your intermediate additions will be stable? Like it doesn't, you know, you don't know when the inputs change?
That's right. So you have no clue, right? There's some time involved. And this is a race. If this will be really fast, I can keep on going like this. And keep on the same value of x over and over and over and over and over and over again. You have no control. You don't manage to order the events. And that's important. If you have a machine, you want to make sure that you step by step, and you want to make sure, as you said, it's only when things have stabilized that you can go to the next thing. When you're still in a transition, and you take the value, you have no clue. Is it 0? Is it a 1? You don't know. So this is one of the main reasons why we're going to need something which is called flip-flops, timing elements, registers into a design. Right. So every single design you're ever going to do has combinational logic where you have basically a direct relationship between input and output. You have the inputs, you have the outputs. If you know the inputs, you know the outputs. That's a combinational logic block. And it's with some delay, obviously. Registers basically keep you values of the past. You can remember things of the past. And this is your typical data path here, where you have a number of blocks here, you get data, you do some combinational logic, you store it, you bring it to the next block, and so on and so forth. And here you can see now I can feed it back. It's only when I put the data in the register that this is going to go. It has to wait for something which is called a clock. We're going to add a clock to help us to be the master orchestrator, the dirigent of the basic orchestra. That's what the clock is. It's the one that sits there. Now you do that, you guys go. Right? That's really important. And we call it registers when it's alone. You put a lot of registers together, it becomes a register file. You put even more together, it becomes a memory. In principle, they could be all the same hardware, but obviously, if I do something, implement like this or this, I might use different circuits to implement them. Because the larger this becomes, the more efficient or the more important area it becomes. Like I say, I need 1 million bits here. Very different than a single bit over there. But you're going to pay. As I said, there's nothing for free. If I want to make something smaller, it's probably going to be slower. Right? This is a trade-off between speed, performance, power, and physical things. All right. So flip-flops you already know. So your basic flip-flop is something that has one input, a D input we call it, and one output which is called Q. Okay? Why Q? I have no clue. It's always been a Q, as far as I know. And this is from when I was an undergraduate student, it was called Q, and it's still called Q. And D, I can understand, is the data input. There's a third input, which is called clock, which is the thing that is going to cause the changes to happen. A flip-flop basically can only change its state when on a clock event. That's the key thing. So what is an event in a particular case of a flip-flop? It is a change of the clock signal. Whenever the clock goes high, we have a transition from 0 to 1. We call it a positive edge of the clock. And that's going to cause, at that point in time, when there's no event on the clock, the output of the register remains the same. Whatever that happens at the input will go up and down and up and down. If the clock doesn't change, nothing changes. It's only when there's a 0 to 1 event on the clock, then we're going to look at the D input, and a little bit later, that's going to appear at the Q. It's not instantaneous, it has some delay. Okay? So you can see here the next one. We see that D is 1. The output goes to 1. Here's him again. Input is 0. Output goes to 0. Here, actually, in between, the input goes up and down. It doesn't do anything, because at the time we see the clock edge, we still have 0. Positive edge triggered flip-flop means that you only react on the positive edge. Negative edge is on the other edge. I can easily build flip-flops that also react on both edges. It's a little bit more expensive to do. But you can imagine you could actually work two times as fast. If I can basically clock things in at the positive edge and the negative edge, I could do that. but it's rarely done. So here my accumulator example here, I already told you, this thing didn't make any sense because I have no clue what you're talking about. I have no clue when X comes in, this races around, just depending upon the delay of the adder. And we don't know how fast the X size comes in, so this is nonsensical. It's like if I write an equation, it's like saying S is equal X plus S. That's a bizarre equation. It says 0 is equal to X. That's kind of what you're saying. You don't know what it means, so it is not making sense. Yes?
Can you go over what exactly the flip-flop made of from basic code?
Can I come back to it in a second? I can tell you how you do that. And there's a bunch of ways of building flip-flops. The circuit guys will tell you, you want to get a fast one, you want to get a big one, you want to get a cheap one, all those kind of things you can do. I'll talk to that in a second, but it is something that, okay. Let's not jump, we'll get there. So here's a better implementation for an ALU. I have an adder and a register, which has a clock. The clock basically is going to change the output of that register when the clock goes high. I might want to have another signal there. How do you start? You don't know what the value is. That's a variable here, SI minus 1, needs to get initial value. So you can reset it or you can set it. So a lot of flip-flops have a set and reset input as well. You can force it to go to 1 or to 0. So what you see here, now we have my load clock. My clock goes up and down. Let's assume that I've done a reset somewhere before. So SI minus 1 is set to 0. S minus 1 is 0, 0. And so my X comes in. Here we go. Every time I get a clock event, right here, I transfer SI to SI minus 1. So you have a clock event here. You see this value goes to here. Same thing, another clock event. This value X here goes to here, and so on and so forth. So clock hits, SI minus 1 becomes equal to SI. And then from the time SI is applied, at that point right after that, let's say here I have SI minus 1 changes. My X change, assume that X changes just after or with the clock. That's an important assumption as well. When do we have a real value at X? Let's assume that happens at the clock, H or just after. So we have X0 here. We add X to it, and we get X0 plus X1. Then clock event happens, disappears at SI minus 1, and so on and so forth. So we have much more orchestrated type thing. So a couple of things you have to know about the clock. One of the requirements of the clock is obviously you only can apply clock events, or the distance between those edges should be long enough that everything in your hardware be allowed to be settled. If I clock it too fast, my hardware doesn't have enough time to do the thing, and you get something which is not finished. So this is your minimum clock period. If you go too fast, if I zoom this too close, that delay, let's say from here, I get X0, X1, you can see there's some delay before the addition happens. You have to make sure that you have enough time to do so. Okay, that's an important thing. Okay, so how would you describe that? Oh, a couple of other details. As I said, your clock, it's kind of bizarre in the order. We haven't talked about logic. If logic obviously has, if I do an AND gate, in Verilog it says X equals A and B. From a pure behavioral perspective, this sounds like something that's instantaneous. I do A plus B, or A and B, and right away you should get X. Not true in reality. Right? If I execute an operation on real hardware, it's not instantaneous. I would love to, but it's not. It has delay. So every logic block has delay. It's physics. You have to charge a capacitor somewhere. A current has to run to a transistor. These things take time. Same thing with a flip-flop. Flip-flop also has some timing parameters. If I apply the clock edge, my positive clock edge right here, it's going to take some time for my output to change, the output to become equal to the input. There has to be some logic you move through. This we call the clock to Q delay. It's the delay from the clock edge to when the D signal is valid, or the Q signal, sorry. The Q signal is valid. Right? So that's one important parameter. Clock to Q is a delay timing parameter. There's some other ones. And I'll explain to you why they're important. Suppose I have the following situation. I have a flip-flop, the Q clock. Here's my D signal. This is D. Here's my clock signal. Something like that. So clock D. So my question to you is, what is Q here? So I have clock, I have my D signal changed exactly at the same time as my clock signal. What should Q be? What should the output be? Sorry? Anybody want to bet?
It's zero.
Zero? One? Yes?
It's undefined. I mean, you can't have instantaneous edges to begin with.
Okay, good. No, you had it totally right. I don't know. It could be any way. It depends upon like a little electron floats by and make the thing flip one way or another way.
Right.
It's purely random. So you're totally right. Simultaneity is very hard, but you could basically be very close to it, right? So we say that when you have a clock edge hat, we take the value of D, but it's unclear because D is undefined at a period of time. So this is a problem. If I have this on a chip, you're toast. It should never happen. So this is why if you basically have a circuit, there's some requirements that we have for my flip-flop signals. We have what's called the setup time. It says setup time is that my clock signal or my signal D has to be stable sometime before my clock edge comes in. So you have to be ready, you have to be done sometime, and then you can apply that clock edge. So the setup time is kind of, you have to be kind of prepare yourself, and then you apply it. But it's also true for the other end, right? Because if I now would take my signal away, I say, okay, it was all beautiful, it was stable, but I'm going to change it right at the clock edge again. That's no good either. You have to go hold it stable for some time after. That's the hold time. Setup and hold times. Now, sounds like a simple concept. It's one of the hardest things to check. Imagine a chip which has 300 million flip-flops, and you want to make sure that you never violate this thing. This is one of the hardest verification problems in chip design. Okay? So this is really crucial thing to remember. So setup time, how long a D must be stable before the rising edge of the clock. Hold time, how long must D be stable after the rising edge of the clock. And the clock to Q delay is a propagation delay. How fast do I basically get the data out? Now you can revert everything for a negative edge as well, right? It's just the opposite. Okay? Good. They're really important. This is going to basically help setting the timing of circuits in a big way. Okay. So my accumulator revisited. So now we have a little problem here still. We're going to add a couple more things. We have the reset signal. Now reset, we can do, when do you do reset and when it's valued? You can basically have flip-flops which have what we call a synchronous reset, and the ones which are called asynchronous reset. The asynchronous reset, from the time my reset signal goes on, I'm going to reset the value of the output. The synchronous, no, 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 no. You're only going to execute the reset at the time of the clock edge. Okay, so you have synchronous versus asynchronous. I'll show you how both of those can easily be described in Verilog. You can choose it. Personally, if you want to play it safe, don't mess around with asynchronicity too much. You only do it at your own risk. When you're really an experienced designer and you have many, many years and many chips behind you, start playing around with asynchronous stuff. Don't do it before it, okay? So obviously X here we also have to think with. Not much added to this. All right. Now, what's in a flip-flop? How do you make something that acts only on an edge? There's a couple of ways of doing this. But the key element that we're going to, actually there's like atoms, right? If you look at an atom, there's other things inside. There's protons and there's electrons. Well, that's true in a flip-flop as well. Every flip-flop somewhere has hidden in there a latch. Latches are actually a more fundamental element than a flip-flop is, if you want to look at the physics component of it. Now, what is a latch? So flip-flops only act on edges. Latches, on the other hand, are what we call level-sensitive devices. It's actually a multiplexer, kind of a multiplexer. What it says is the following thing, that a latch, here we have this, is another gate that has 3 inputs, just the same, D, Q, and C. But now the result is different. A latch says when the clock is low, we're going to put this latch, the output Q is going to be constant. It's not going to change. It's fixed. It's stored, it remembers the old value. We call this the hold mode. So you hold the old value. On the other hand, when the clock is high, when the level of the clock is high, the input of the latch is equal to the output. It just becomes a gate. The input goes in and goes straight to the output. Okay? So this shows it right here. Clock is high. You can see D comes in, Q follows exactly a little bit later. If D goes up and down during a period of time, Q goes up and down. Now, clock here, you have D goes high, Q goes high, the clock goes low. A little bit later, D goes low, nothing changes on Q. Because the clock is low, it just keeps on holding its old value. Very simple element to build. Latch is nothing else than a feedback circuit. The simplest version of a latch is this. So we build memory elements. We take 2 inverters and you connect them back to back. As you can see, if this is 0, this is 1, this is a stable situation. This network makes sense. And it's stable. And the same thing if I put a 1 here, you get a 0 here. And it will remember this as long as this is valid. Now I can change the value. You have to have means of changing. Well, to change it, I might have actually a switch coming in here to force it, and then I open that feedback loop for a little bit. But basically, to remember, we're going to come back to that later, a latch is a feedback system. We use feedback, positive feedback, to basically force the network into a 1 state or a 0 state. It's called bistable. It has only 2 stable states. Either it's a 1 or it's a 0. And you can make it flip, but that takes energy. Okay? So latches are really simple things. Now, latches are level sensitive. This type of thing is level sensitive. So how do I now build a flip-flop out of a latch? Something that only can change on an edge. Any suggestions? Yes?
Connect 2 of them.
That's right. It's called, you basically take 2 latches and you clock them on opposite faces of the clock. So as a result of that, there's never a path that goes all the way through. Right? When one is on in transparent, the other one is in hold. Hold, transparent, transparent, hold. They switch. Master-slave is one option. Other approaches. If I take a latch, same thing here, and I make a special clock, a very narrow clock, really narrow. It's a pulse. It comes in there, it pulses it. It means that this thing can only change when it goes in that mode. It's going to take the value, puts it out right away. This is called a pulse-triggered latch. Same thing. You can build a master slave or a register using pulses as well. And some of the fastest ones are built that way. And really high-performance design, that's what we do. So that gives you some insight. The question is, how do you build a flip-flop? Well, that's what we do. Okay? There's some other tricks, lots of other tricks. There's 100 million papers on latches and registers, so I'm not going to go there. Okay? Positive edge trigger flip-flop is built from 2 level sensitive latches. Okay. Now, let's get back to Verilog, because now we want to get it in there. We're going to use always blocks. Always is going to be essential because, think about it, a latch or a register is an edge-triggered, is basically a event-driven thing. It says, when something changes on the clock, we're going to do something. The always block is really good for that. So here's a couple of examples, just to put things in contrast a little bit. You have AB, this is a multiplexer. If always add star, I haven't talked about star yet. This is for lazy people. If you don't really want to enumerate all the inputs that basically can matter, this thing is star. Is there any signal that changes that basically matters? I'm going to evaluate this thing. If select is equal to 1, select A, otherwise B. So this is a typical always block in combinational. Here's a one that's used for sequential. I'm actually going to now use a D flip-flop together with a multiplexer to describe this circuit. So we use a always block, but here's an important one. We say always as positive edge of the clock. So only when the clock has a positive transition will we evaluate this. Otherwise, the value remains the same. Yes?
I noticed that A and B aren't in the sensitivity list for always. So does this?
It does. I don't care what's happening with A and B.
Okay.
It said this is only going to be triggered. It's not when A and B are changing. Remember, this is a flip-flop. It's only when the clock changes that I'm going to evaluate this.
So you don't have to pass them into
No.
the edge.
No.
Okay.
Because what this says is, what are the signals I'm watching for? What are the things that are going to cause changes? In this case, it's only a positive edge of the clock that's going to do, at the positive edge of the clock, I'm going to basically evaluate this network. And then you can write it there, if select out is equal to B, else out is equal to A. Now, another thing to observe here. Another little semantic or syntactical thing that's snuck into it. If you look left and right, if you look in this block here, multiplex description, there's another difference.
Blocking and non-blocking.
That's right, it's blocking and non-blocking. It's an arrow. This is an equal, this is a statement. This basically says, I transfer this value B to A. It is, anytime I have something with a flip-flop output and you have something with a positive, that's a sign of the clock, you have to use this. Okay? And there's a difference between the two. I will show you in a second. I could write equal, but I might have unintended consequences. I'll come back to that in a second. But notice that there's a change here. So flip-flops and edges, now it's easy to describe it. A flip-flop is always at positive edge of the clock, begin, transfer D to Q. Done. That's my flip-flop. Latch is a little bit more complicated. It says always at clock or D. Because now, as I said, there's actually two things here. It's clock events can happen or D events. So if we look at if anything changes or clock or D. If the clock is high, we transfer D to Q. If, on the other hand, the clock is low, nothing happens. Q remains its all value. So it's a very simple description here. Now you notice I don't use positive edges or here or anything at all. Okay? So your latch, your flip-flop. Fairly simple to be describing using the always block. Now I can do all kind of other games. I can add a set or reset. I can make it synchronous or non-synchronous. Here, for instance, I said at positive clock, this is a set reset. It means that when I set reset, it should go to 0. You can see here there's only one definition, it's positive clock edge. So this is going to be a synchronous reset, right? It's only when the clock goes high that I say, oh, by the way, I said we're going to put it to 1 or 0, or otherwise we just take the old value. If you would want to make it asynchronous, I make a small change. Oops, was that there somewhere? Yeah, here's my asynchronous. I say if positive edge clock or negative edge clear B. When there's the clear signal goes down, or in this case it's the clear B is an invert signal. So when the clear signal, yeah, when there's a negative edge, when the clear signal goes low, or the clear B signal goes low, we're going to do a clear. So you can see this is asynchronous. This block will be evaluated on the clock clear signal going down. Right? While here, it's only on the edge of the clock. Right? Now another kind of bizarre thing, but it makes sense. It's a result of their whole strategy. You know, for registers and things like that, I need to use those edges. Once I define something based on edges, everything has to be based on edges. So you cannot write, for instance, always add clear or positive edge clock. So you cannot mix the two. I cannot have edge-based or base type of sensitivity list combined with level-based. They're either one or the other one. Okay? So that's why I have here negative edge clear B. Okay? Now, a couple of rules. If you have always blocks and you have a number of them, be careful, you should be careful. Like one thing you should never do is have the same variable defined in two different always blocks. Because they actually evaluate simultaneously, I cannot predict what the result is going to be to you. It could be independent. So never do that. Keep things clear, keep it modular, don't spread your code all around. And always blocks with the same trigger execute concurrently. Concurrently can be dangerous, right? I have two blocks. I have block here which says always at positive edge clock. And just below the, I said always at positive edge clock. Those are going to execute at the same time, simulation-wise. And the hardware is a little bit different, but the simulation, they're going to execute at the same time, which can always create same things. So be aware of that. So always blocks are, as I said, they're a potential bug source. Okay, one more bizarre thing. Well, actually, it's not bizarre, but it's an important one to know. Non-blocking versus blocking. It's my arrow versus my equal sign. What a non-blocking statement does, that's where you have the blocking statement, the equal statement, basically says it's an equation. It says evaluation and assignment of a variable are simultaneous. They happen immediately. I say A equal B plus C. A is immediately equal to B plus C. With my little arrow thing, so like here I have an example. I can write down always at star x equal da-da-dum. Here, obviously, we're going to simultaneously evaluate all of those three. They happen all at the same time. No reason to worry. I could also write it this way. I could put arrows here. Right? Instead of equal signs, I put arrows. It's the same description otherwise. But there's a fundamental definition here, change here. This here, as I said, is instantaneous. This is the assignment of A or B to X, and A or B and C are only done at the end of the simulation step, after they all have been evaluated. So we first do, it's like a two-step operation. in this case, you compute all the values, and you store them in temporary things. And then when everything is done, then all at the same time I make X, Y, and Z. Now, would that make a difference here? No. But suppose I make this a little bit different. I replace C by X, which I could, right? X equal A or B, and I say Y is equal A, X or B, X or X. I could do that. Now you're going to see a fundamental difference between this and this. Because I write equal, then I'm basically going to put this expression right in here. While here, we're going to evaluate all the expressions, and then when we're done, we're going to give the new values. So I'll show you an example of how this, it's a beautiful example. It's a very common circuit. It's called a shift register. Right? Basically going to take an input, and I have a number of flip-flops, and I just clock, 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 and it goes through. Right? It's a delay line of 3 bits. So we have 2 descriptions, identical. Says, okay, we have 2 registers, we have input and a clock, we have an output, and we have 2 intermediate registers, Q1 and Q2. And we write down here, always at positive edge clock, and we do here non-blocking, and I here use blocking statements. That's the only difference between the 2. Which one will implement my shift register? Left on, right? Because here, what you're going to say, well, in is equal to Q1, Q1 is equal to Q2, Q2 is out. Actually, out is equal to in. That's effectively what I'm going to get. The input is going to go brrrt, right to the output. Well, here you say, okay, I'm going to basically take all the values, I'm going to ready, and then at the same time, you assign them all to the output values. So the non-blocking is typically what you use for sequential circuits. You can do this, but it's scary. Yes?
What kind of circuit will the put on the right generate?
Sorry?
What kind of circuit will the put on the right generate?
Let's see what it gives you. Let's see what we have. We might have. Very interesting circuit. It has all the same values. It's just a little flip-flop. That's all. Maybe that's what you want, but it was a lot of writing for nothing. Right? So, no. So, again, use non-blocking primarily. Yes?
If I reverse the order of the statements, like I write out equal to Q2 first and the Q1 equal to in last, then it should work correctly, right?
Doesn't matter. I can, the order of the statements.
No, for the block.
For this one here? Oh, yes. Well, let's see. No. It's only the dependency between the signals. Right? It says in is equal to Q1, Q1. I can change the order of the equations here too. I will still get that bizarre circuit. It doesn't matter. It's not that we evaluate these things in a row. It basically says if you adjust this set of equations, out is equal to Q2, but Q2 is Q equal to 1, so I get out is equal to Q1 is equal to Q1 is equal to in. That's my statement. This one expression that said they're all equal. That's really what we're saying. And in the end, there's going to be a flip-flop that basically clocks it. Okay? All right, non-blocking. Okay, so just to kind of cap it up, this is a nice little example of what we can do. Suppose, for instance, I want to build a four input counter or 4-bit counter. So what we have is basically a circuit that's at +1, and we have a couple of control signals. You have to have a clear signal. When the enable is low, the counter doesn't work. When the enable is high, the counter works. And we have one flip-flop of 4 bits, a register of 4 bits wide. So synchronous clear. You can see how it compares. This can be described in a very dense manner. Always at positive edge of the clock. It's all synchronous. You only do things when the clock happens. Then count is equal to, if it's clear, so again, this is one of your, it's clear, then it's 0. If it's not clear, we look at it's enable. If it's enabled, we increment. If it's not enabled, we just keep the value. That counter is done. So fairly straightforward to describe those things. And here another one, the last example, another cute one, is parallel to serial converter. We use that often, right? Suppose you want to go on a chip and you do everything in parallel, and then you want to go off chip and you want to have a serial link. You want to translate that parallel word into a serial set of bits. So you have a parallel feed, 4 bits in parallel coming in, x0, x1, x2, x3. So when you have when the clock, there's two modes when you do a load statement. Oh, yeah, here you go, input load. That's right there. When you load, you feed the 4 inputs into the shift register. And when then the load is low, you clock and the bits come out. To make it a little bit more interesting here, what they do and say, okay, when the last bit is, what's happening with the last bit, we feed it back into the first bit. It's actually a circular shift register. You could do it any other way. But this is what it describes. You have this intermediate signal, NS, which is your state variable. So we define a number of wires, NS. And it says when the load is high, then we load in X. Otherwise, we just do that rotation part that I was just describing. And then over time, the positive edge clocks goes, NS goes to Q. So this is the logic. This is the transfer into the registers. Very nicely, basically separating the sequential part from the combinational part. And then finally, you have to set the output bit to something. Well, that's what's that. Okay? All right, that's all what I have on that. Next lecture, we're going to go back a little bit about combinational logic. I assume a lot of you have experience with Boolean logic. I'm not going to spend a ton of time on it because I assume you know this. Who has never heard about, or who has heard about De Morgan? De Morgan's law, okay, good. So, okay. Who knows Carnot maps? Okay, so good. So we can go quickly through that as well. I'm going to go. So by the way, why would you use Carnot maps? Why are Carnot maps a good thing to do?
Simplify circuit.
Simplify your circuit, yeah. But I can also describe it as Boolean equations and do Boolean manipulations just as well. No, I think my good reason for this is only one. Humans are really good visually. Half of our brain is our visual cortex. So master of brain is basically on vision. We know how to recognize patterns really well. Manipulating equations and say, oh, this and this and this, and then you can apply this simplification here and this simplification there. It gives you the same thing. But if you can see a pattern and you look at it, oh, there's a bunch of zeros together here. I can put a big square around it. Done. It's really good for basically, it really is a simple way of doing things. Now, has you ever tried to do a Carnot map with more than 4 variables? Like a 6-variable Carnot map. You have to think in n dimensions. Doesn't work. Or again, our pattern matching thing only is limited to certain things. And ultimately, you know, synthesis tools do a really good job. But it's important that you understand all those representations. There's different ways to describe logic, and that's what I'm going to stress on. And basically say, how do I know how can I prove that A is equal to B? That's the most important part. And as I said, I'm going to go very quickly to this because I don't want to spend a lot of time on things you already know. And there's some work in the homework that is going to refresh it for you, for those of you kind of say, oh, yeah, no, but it's been in the past. All right, so no class on Monday, and then we see each other on Wednesday.